In this video, we are going to discuss a method for approximating solutions of certain type of differential equations that is called Euler's method. So we consider an initial value problem like the one I'm going to write here. So let's say we have dy dx is equal to f of xy. And we also have an initial condition. I said it's an initial value problem. So let's say we know y at x0 takes the value y0. So the idea is that we are going to approximate the value of the solution at some point, let's call it x star. I will draw a picture here. So first let me write that what we are trying to find out is what is the value of the solution at some point x star. That's what our goal is. So I'm going to mark in my picture point x0, y0. We know that we want the solution to go through that point. And we do not know how the solution looks like, but I'm going to anyways draw something. Let's say this is the solution. And we're trying to find what is the value of the solution at this point x star. So this is the idea of what we're going to do. At the point x0, y0, we know the solution goes through there. We can consider the line tangent to the solution at that point. It's going to draw in a little tangent over here. And then we could move through that tangent to our next point a little bit farther. Let's say we call that point x1. And then we can look at what is the value of the tangent at that point. We don't know what is the value of the function at that point because we don't know what the solution is. But if we move on the tangent, so if we look at the value of x1 and the tangent, that is going to be close to the value of the function at that point. So this is going to give us a new point y1. We do not know exactly what is the value of the solution at x1, but we know that the point y1 is close to it. Now look at this. The secret here is that we do not know what is the value of the solution at x1, but we could find what is the slope of the solution that goes through that point. So we could find what is the dy dx evaluated at x1, y1. And we can do it because this is the value of the function at x1, y1. So that means if we know that derivative, we can draw a little tangent line at this point as well. And we can repeat what we did before. We can move along the tangent line to a next point, let's say x2, and we can check what is the value of x2 at the tangent. We don't know what is the value of x2 at the function because we don't know the function, but we know that the tangent is approximated, so this new value y2 is close to it. We repeat this, so we keep moving along little tangent lines and taking small steps towards x star. And on each step we say, well, too bad we don't know the value of the solution, but we can approximate it with the little tangent from step before. If we keep doing this, we are going to get to an approximation of the solution at the point x star. This is the idea of what we're going to do, and now we are going to write what those steps formally look like. So we start with the point x0, y0. That's our first step. The next step, we are going to take a point that is x1 equals to x0 plus h, where h is the smallest step that we are taking towards x star. And we define a new point y1 that is going to be given by moving along the tangent, and that will be in an equation. We are going to look at y0 plus h times f of x0, y0. Let's look at what I wrote over here for 1 second. This is the result of evaluating the tangent function at the point x0 plus h. Let me write here the equation of the tangent function so I convince you of that. So the tangent function is going to be y minus y0 is equal to the value of the function at x0, y0, that's the derivative, times x minus x0. So this is the equation of the line tangent to the solution at the point x0, y0. Yeah, the slope is given by the derivative. Remember, this is the same as the value of the derivative at x0, y0. Yep, so if you look here, when I evaluate for the value of x equals x0 plus h, the x0 cancel, and that's why I got this value h over here. So I hope I convinced you that this is the next step. So this is the result of evaluating the tangent line that is purple in our sketch at the point x1. So now that we have the point x1, y1, we are going to repeat for the next point. The point x2 is going to be x1 plus h. So we are moving towards x start, another small step h. And this is the same as saying that this is x0 plus 2h steps. And the point y2 is going to be given by, we need the y1 from the previous step plus h times the value, the function f evaluated at x1, y1. This is the result of evaluating the line tangent that is green in our picture at the point x1. Sorry, at the point x2. We are going to do this as many steps as we need until we get to the point x start. In general, let me write here, need to get a little bit more space, but yeah, let me write here that xn is going to be given by x0 plus n times h, so that's how many steps I need to take, and then yn is going to be given by the previous y plus h times the function evaluated at the previous point. So f evaluated at xn minus 1, yn minus 1. The good news I have for you at this point is that actually I'm copy pasting this. This is in the formula booklet. So you need to understand how the method works, but you don't need to remember by heart how to obtain the steps. And we are going to see an example of how to apply this in the next video.